Hello, I'm Nuno Carvalho, and today I'm going to be giving my worked out solutions to the 2004 AP Physics C Electricity and Magnetism exam. I hope you enjoy my video. I hope that you find it useful. If you want to also see my solutions to the 1993 multiple choice exam, I've made that video in the past as well, and you can find the links to these exams and answer keys in the description. Enjoy the video. Starting with number 36, we are told that we have three 1.5 microfarad capacitors that are connected in series, as shown in the diagram above, and we want to know the capacitance of the overall combination. So I'm just going to write here 1/2, and I'm going to omit the microfarads for now. We'll just add them in at the end. But what we need to know here is that we have capacitors that are added in series. And so how do we how do we get to the equivalence capacitance of capacitors added in series? Well, we use this formula here, and we would keep adding if we had more capacitors. But so it's 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2, and so on. So we just plug in the values that we have here, and we're doing 1 over 1/2, which really is just 2. So we're adding 2 a bunch of times. And so what this will tell us is that the equivalence capacitance is 1 over 6. And let's not forget here the microfarads, and so the answer is E. Number 37, we're told that a hairdryer is rated at 1,200 watts and 120 volts. And we're asked about its effective internal resistance. Really, all we have to know is the formula for power. And so in your formula sheet, you're given this right here. And then we can use the fact that I is equal to V over R. And so this is from Ohm's law. To get that power is also going to be equal to V squared over R. Okay, now we take this and we solve for R, which is to say that R is equal to V squared over P. And it's just a matter of plugging in our values. And what you'll get is that the resistance is going to be 12 ohms. So the answer is C. Number 38 is a tough problem in my opinion, one that I struggled with as a student of electricity and magnetism. But I think now I have a better understanding of what's going on here. And the best way to explain it is by thinking about this conducting spherical shell as a Faraday cage. And so if you don't know what a Faraday cage is, it's just any conducting material that surrounds a region. And what it essentially does is, since it's conducting, it will basically insulate the inside from the effects of electric fields that are on the outside of the shell. And that's because uh, the electric potential inside of a conductor must be the same anywhere inside the conductor. And with some thought experiments, you can figure out why that would mean that only the inside really matters when it comes to figuring out the electric fields inside of it. So all this is to say that the only thing that would matter for the electric field felt at point P would be Q only, because that's the only charge that's inside of this Faraday cage. In number 39, we're told that in a certain region, the electric field along the x-axis is given by this function here with these constants. And we're asked about the potential difference between the origin and x is equal to 0.5. Okay, so the relevant formula here is going to be that voltage is equal to the negative integral of E dx, and we can already put in our limits of integration here, since we're going from the origin, which is x equal to 0, to 0.5. Those are going to be our limits. And then it's just a matter of plugging in the formula here for the electric field that is given by this function. So ax plus b, we can already just put in the constants that they give us. And then it's just a matter of very simple calculus. Integrating this, you'll get 20x squared plus 4x. And remember that we are integrating from 0 to 0.5. And if you work this out, what you will get is that the voltage difference is going to equal to -7. And so our answer is B. In number 40, we're told that a particle of charge plus E and mass m moves with speed v perpendicular to a uniform magnetic field B directed into the page, and we're asked which of the following correctly gives the direction of motion and the equation relating V and R. So let's start by first thinking about the direction. If we were to imagine a positive charge moving in that direction, we can use the right-hand rule to figure out that the force that it would feel would be like that, sort of to its left. And so with that in mind, it only makes sense that the motion here is going to be counterclockwise. That's the only possibility given this field. So we can already eliminate A and B. And so now we're left to think about the equation. So what is going on here? Well, we need to start thinking about the forces that are acting on this particle of charge, and it's only going to be the magnetic force here. But what you'll see is that since this is moving in a circle, this is called a centripetal force, and it's something that you might remember from mechanics when you learned about rotational motion, for example. And what you might remember from that is that this means that instead of your typical ma, we use this little c here to denote centripetal acceleration. And centripetal acceleration is equal to v squared over r, where r is its radius of motion, or radius of revolution, I guess. And so plugging this into this formula and also plugging in the fact that fb can be given by qv cross b, and since they're perpendicular to each other, we can just say b like that. And let's also plug in that Q is equal to E. We would be left with E times V times B is equal to M times V squared over R. Okay, so we can cross out that V and just take away 1 power of that, and then we would move over the R to that side, and we would see that we'd be left with E times B times R is equal to MV. And so the answer from among these is going to be C. In number 41, we're still working with the same setup from before, but now we're asked about the period of revolution of the particle, and this also takes a little bit of knowledge from mechanics. You might see in the formula sheet on the left side that t, which is the period of revolution, is equal to 2 pi over omega here. And if you multiply both the top and bottom by r, you can also write this as v, and so now we have that the period is equal to 2 pi r over v. And this is good because we know the formula for v. Well, you do know it if you got the previous problem correct. So it's sort of a multi-part question here. So we can solve for v here, saying that it's equal to EBR over m, like that. And then it's just a matter of plugging all this in to get that t is equal to 2 pi r m over EBR. And so the r's cancel out, and we're left with 2 pi m over EB. And so the correct choice is C. Number 42 is a very straightforward problem. We're asked a 20 microfarad parallel plate capacitor is fully charged to 30 volts. What's the energy stored in the capacitor? Well, we just need one formula, and that's from our formula sheet, and that's that the energy stored in a capacitor is given by 1/2 of CV squared. There's also a form of this that is 1/2 QV, but since we don't know the charge, we don't use it. We just need this. And then when you plug in 20 for the capacitance and 30 for the voltage, what you'll get is that the energy stored here is going to be 9 times 10 to the negative 3, and that's in joules, and so the answer is B. Number 43, we're told a potential difference V is maintained between two large parallel conducting plates, and an electron starts from rest on one plate and accelerates towards the other. And we're asked about its speed as it reaches the second plate. We're asked about what that speed is going to be proportional to. And so this is actually a conservation of energy question. So let me write here the formula that hopefully you remember from mechanics. Okay, and we can already say that the initial kinetic energy is going to be equal to 0. The final potential energy will also be equal to 0 because its potential difference at that point will be 0. There will be like any other place that the electron could go to. And so what's left is plugging in these formulas here that are from your formula sheet. And then let's just solve for V. So V squared is going to be equal to 2 times EV, I'm plugging in E for Q here, over M, which is to say that V itself is going to be the square root. And so if we're being asked about what the velocity is proportional to, well, here all the answer choices contain V in them, so let's think about what V is. V is square root on the numerator, so our answer is going to be that, which means the answer is C. In number 44, we're told to apply Ampere's law to this situation where we have a current of uniform distribution over some wire of radius r, and we're asked about the magnetic field felt inside of that wire at a distance of little r, which is going to be less than big R. Okay, so Ampere's law states that the integral of B dot dl here is going to equal to this constant here times the enclosed current, and so this here is actually going to be sort of the key part. Well, there's two different parts here. I believe that this side of the equation is easier to get to. What we have to imagine is that if we have some current here, and imagine the current sort of coming out towards us, so it would look like that. And then we're selecting a circle here, similar to Gauss's law, how we create a Gaussian surface. Here we're creating sort of a, I don't know, Amperian loop, and this loop is going to have a radius of little r. And so the length of this radius, or this loop, is going to be 2 pi r. And so this right away eliminates d and e from our answer choices. And then we need to figure out what the enclosed uh, current is going to be. And the way to really think about it is if it's uniformly distributed over this cross-sectional area, then really we can just say that we can just sort of find what's the proportion of charge, or of current, I should say, on this circle here compared to the overall circle. And so that means that we're looking at pi little r squared over pi big R squared. And so the pi's cancel out. And then we would have to multiply this by I. And hopefully this makes sense to you, because if the little r was big R, which means we'd be enclosing the entire wire here, then what we'd get is 1 times the current I, which would mean it's the entire current. So hopefully, again, that makes sense to you. And so now it's just a matter of plugging this stuff in and comparing to our answer choices. Seems like B matches it perfectly. In number 45, we're given here two charges, Q and negative 4Q, at two different spots, and we're asked about the direction of the electric field at point P. And this is really just a matter of thinking about each chart or each electric field vector independently and then summing them. So let's think about Q here. It will be pointing away from this point, and so let's draw an arrow like right there, parallel to sort of the line that connects Q and P. And then thinking about the negative 4Q, since it's negative, it will be pointing towards the direction of the charge, and because it's negative 4Q, we should expect it to be like 4 times the magnitude of that first vector that we drew. And then summing them, since we just sum electric vectors to get the overall electric field vector at a point, you can clearly see that this is going definitely to the plus x direction, but also a little bit to the negative y direction, and so the correct answer choice is going to be E. For number 46, we're still working with the same charge distribution from before, and we're asked about which of the labeled points on the x-axis the electric field is going to be 0. Well, we don't want to be testing every single one of these points. We don't have the time. So we want to make some quick educated guesses about which ones it's not going to be. So let's think about C and D. Since these are in the middle, in between, or by middle I mean in between the two charges, let's think about the electric fields that each charge is going to produce to anything that's here in between them. So the positive Q will make a charge going in that direction, and the negative Q will make another electric field vector going in that direction. Which is to say that definitely we're not going to have an electric field of 0 in between the two charges, so we can eliminate C and D. Okay, what about E and A? Let's just compare those two. Which one is it more likely to be? Well, we know that the electric field is going to be proportional to, well, actually, I can just write the formula here, like that. And so these 2 points, A and E, are sort of symmetrical, except that we have a stronger charge here on the right side. And so because of this r squared situation here, what's going to happen is that the attractive force felt on point E in that direction, and excuse the work from the previous problem, let me erase it. The attractive force on point E, because of the negative 4Q charge, is going to be definitely stronger than the repulsive force from this charge, so we know that E is also not going to be it. And so we're left with A and B. So that means that our electric field of 0 must be somewhere in this region. And at this point, it does take a little bit of testing out the two situations. And so let's start with point B here. And let's just imagine sort of how this would look. And I'm going to count each tick mark as just a, I guess, 1 meter. So the electric field overall is going to be adding the repulsive force from the Q charge and the attractive force here from the negative 4Q charge. And so let's start with the negative 4Q charge. We are going to have negative 4Q. Actually, let me treat this as positive, and we'll say to the right is going to be a positive vector. And we multiply this by k, and then we have here a distance of 5 squared. And then the repelling force to the left is going to be given by kq over here it's going to be just 1 squared. And is this going to equal to 0? No, it's not going to equal to 0. Okay, so it's not going to be that, and we can already sort of assume it's A, but let's just work it out here. Using the similar logic from before, what we'd be doing here is k times 4q over, and now the distance is going to be 8 squared. And here, actually I should still be subtracting here, we'd have k times q over, and the distance now is 4 squared, and this is going to equal to 0. Let's move over this to the right side, and we'd end up with something like this. Let's cancel out the k and the q, and what we'd be left with is 4 over 64 equaling 1 over 16. Is this true? Yes, it is, and so the answer is A. Number 47, we're given a circuit, and we're told that when the switch S is open in the circuit shown above, the reading on the ammeter is 2 amps. And then we're asked about what the reading on the ammeter is going to be when the switch is closed. Well, an ammeter measures current. That's the first thing to know. And it's measuring current out here, by the way, so not inside of our parallel situation here, so we don't have to worry about that. And so how does current relate to resistance? Well, it goes by Ohm's law here, which is in your formula sheet, and it's something you should have definitely memorized, which is to say that if the current is going to change, it's going to be sort of an inverse relationship to the change in R. Okay, so then we need to figure out what the overall equivalent resistance is going to be. So when the switch is open, the current is just going through here, which is to say that the equivalent resistance is just 35 ohms because it's in series. But when the switch is closed, we now have two resistors here that are in parallel, and so we need to use this formula here, also in your formula sheet, to figure out the overall equivalent resistance of these two right here. And when you work it out by plugging in these values for R1 and R2, you'll get that the equivalent resistance is equal to 15 ohms right here. And so we have in one situation, in the first situation where it's open, the equivalent resistance overall, adding here the 15 ohms, is going to be 35 ohms. And then when it's closed, it's going to be just 30 ohms. Okay? And again, using this relationship right here, it seems like we are decreasing the resistance when we close it, which means we're going to be increasing the current. So we can already limit C, D, and E, and then comparing whether it doubles or just increases slightly. Well, to double the resistance, we'd have to, to double the current, we'd have to be halving the overall resistance, which is clearly not what's happening. So B is the right choice here. Number 48, we're told that two conducting cylindrical wires are made of the same material. Wire X has twice the length and twice the diameter of wire Y, and we're asked about the ratio of resistances of X and Y. So starting with the resistance of wire Y, we know from our formula sheet that the resistance is given by the resistivity times L over A, where A is the area, the cross-sectional area of the wire. And so then we can use the fact that areas of a cylindrical wire is just going to be pi r squared here. And then we're told that Rx is going to have double the length, but it will also have double the diameter, which means double the radius, which means what's happening here is going to be 4 pi r squared. Okay? And so simplifying this is going to be 1/2 of PL pi r squared. And as you can see, this right here is just ry, which is to say that rx is going to be 1/2 of ry. And so then when you work out the ratio, you'd get that it's going to be B. Number 49, we're told that a solid metallic sphere of radius r has charge q uniformly distributed on its outer surface, and we're told a graph of the electric potential as a position or as a function of the position r. And so then we're asked about the same thing, but for the magnitude of the electric field V. Okay, the key word here is going to be metallic, which means a conductor. And the electric field inside of any conductor is going to be 0. Okay, so we can already eliminate A and B. Also, you can tell by the fact that E is equal to negative dV over dx. In this case, let's actually use dr here. That since this here is constant, the derivative is going to be 0, so you should expect a 0 for, oh, sorry, E is also going to be canceled. So we're actually just down to C and D. And so comparing the two, what's the difference between them? Well, E seems to, or C here seems to slope down faster than D. It's sort of, I guess, I don't know, more concave or something. And this is all to do with the fact that we're taking a derivative of v, where v is going to be proportional to 1 over r. And you can tell this from your formula sheet, but also because it tells you here that it's a metallic sphere of charge q uniformly distributed on its outer surface, which means we can treat it like a point charge. And so we can use the formula for the voltage of a point charge, which well, it's proportional to 1 over r. And so taking the derivative of that with respect to r would tell us that E is going to be proportional to 1 over r squared, and r squared is sort of going to be um, more concave than 1 over r, which is to say that C is going to be the correct answer here. Number 50, we're told two parallel wires, each carrying a current I, repel each other with a force of F. If both currents are doubled, then the force of repulsion is going to be what? Well, if we have two wires that will be repelling each other, well, first of all, we know that the directions are opposite, but actually that doesn't really matter. What we need to be thinking is about the magnetic field that they exert in the position of the other, and then the magnetic force that will happen because of that magnetic field. So to begin with, uh, you can use Ampere's law here to figure out if there are two long wires, that is. You can use Ampere's law here to say that B, the magnetic field due to a current I, is going to be given by this formula right here. And then we can use the formula that F of B on a current carrying wire is going to be given by I times dlxb, and we can really just simplify this since these magnetic fields will be perpendicular and also will be constant, to say that it's going to be equal to ILB. And by the way, this current I is the same as that since they have the same current in this scenario. So plugging this now all in is going to be that FB is going to equal to this right here. And so then you can see that doubling the current, right? We're doubling both currents, which means that we're doubling current on both wires. Uh, this will become 4I like so. And we're still squaring this since we're just doing 2I and then we're squaring that, which is to say that the overall force will be 4 times what it was originally. Number 51, we're told a circular current carrying loop lies so that the plane of the loop is perpendicular to a constant magnetic field of strength B. And we're told suppose that the radius r of the loop could be made to increase with time so that the radius is equal to a times t. And we're asked about the magnitude of the EMF. Okay, well then we can look at our formula sheet and we know that EMF is given by, well, let's just worry about the magnitude so we don't care about the sign, is going to be the change in the magnetic flux with respect to time. So what is the magnetic flux? Well, the magnetic flux, once again, from our formula sheet, is going to be given by b dot dA, the integral of that, that is. And in this case here, since the loop is perpendicular, we don't have to worry about the dot product. We can just multiply, and also it's going to be constant, so we can just say that it's equal to BA. Well, A is changing. B is not. B is consistent here. It's constant, but A is changing, and well, since A is equal to pi r squared, and we're told that r here is equal to AT, then that means that A is equal to pi, then A squared times T squared. Okay, so then plugging this back in, we have that the magnetic flux is equal to B times pi times A squared times T squared. And then this is just calculus. Take the derivative of that, and you'll get that the derivative, which is really the magnitude of the EMF, is going to be 2B pi A squared T. And from our answer choices here, that's going to be A. Number 52, we're told that the figures above show two parts of two circuits, each containing a battery of EMF and an internal resistance R. And we're told that the current in each battery is the same as 1 amp, but the direction of the current are opposite, so on the two circuits here. And we're also given the potential differences across the battery's terminals as 10 volts and 20 volts. And then we're asked about the values of the EMF and the R. Okay, and so this requires a good knowledge of Kirchhoff's rules and how we can use that. And so the way I would think is, let's just say that here the negative side will have a voltage of 0 and the top side will have a voltage of 10. And so same thing here. Okay, and we want to go in the direction of the current. At least that's how I like to do this. And so starting with, let's figure out the formula that's going to be given for that's going to involve, I guess, the EMF and the R, starting from here. And so we start with the 0, and we're going to go around like that. And let's just sum the voltages that we come across. So first, we're going down a resistor, which means that we're going to be subtracting uh, I times little r, and since I here is just 1 amp, it's just little r. And then we're going to go up in voltage of the EMF of the battery, which means we're adding this right here. And then we get to this point, and we know that the voltage at that point is going to be equal to 10. So there is our first equation here. Okay, let's do the same thing now, but we're going in the opposite direction of the current. And so we're starting with a voltage of 20, and then we're going to go down here, and we're actually going down the battery, which means we're subtracting out the EMF. And then we're going to also go down the resistor, which means we're doing I times little r, which is to just say minus r, because the amps is 1. And this is going to equal to 0, because that's this at this point right here. And so then let's just solve this now to say that the EMF plus R is going to equal to 20, and we also have that this up here. And so let's solve here for, I'd say EMF is maybe easier, and then let's solve this for EMF, which is going to be 10 plus R, and then it's just a matter of setting these two functions equal to each other. So again, I just got this from here, and then this from here. Setting them equal to each other, we get 10 plus R is equal to 20 minus R, which is to say that 2R is equal to 10, and so R is equal to 5. And we could already just select our answer here, but let's just check that with 5 ohms, this makes sense that it would then give us 15 volts, and this makes sense that it would give us 15 volts. So C is definitely correct here. Number 53, we are told a charged particle can move with constant velocity through a region containing both an electric field and a magnetic field only if and then we're asked here to evaluate a bunch of statements. So if a charge, and let's just imagine it's positive, is moving with a constant velocity here to the right, and let me not connect so that it doesn't look like it's a force, then that means that the net acceleration is going to be 0, right, since it's a constant velocity, which means that the net forces are going to be 0. And so if it's in an electric field and a magnetic field, then we imagine that it's facing a electric force, and so therefore it must be facing a magnetic force in an opposite direction, but equal in magnitude. So what conditions are going to create this? Well, then what we need to be thinking about is what's the direction of the magnetic field that would cause this scenario here that I drew out. And if you use the right-hand rule, what you'd get is with a charge moving to the right and experiencing a force down, it must mean that, let me figure this one out myself. Okay, that means that the magnetic field must be pointing up, or not up, but I guess out of the page, like so. Okay, and so with this drawn, let's now evaluate each of these statements. So, can the electric field be parallel to the magnetic field? No. Clearly you can see that the electric field, which by the way I should mention would be going in the same direction as the as the electric force, it cannot be in the same direction as the magnetic field. So A cannot be true. B, the electric field is perpendicular to the magnetic field. Well, that's certainly true. That's what's happening here. So let's not cross it off. This seems true, but is it always going to be true? We'll have to think about it. The electric field is parallel to the velocity vector. This is not true because then we wouldn't be able to cancel out with the magnetic force. The magnetic field is parallel to the velocity vector. No, because then the magnetic field would not be exerting a magnetic force on the charged particle, since the cross product would be 0. And then E, the magnetic field is perpendicular to the velocity vector. Well, in this drawing here that we drew, this is also true. So we run into this issue that we have two statements that are currently true with our drawing. But let's think about it a little bit deeper. With E here, the magnetic field being perpendicular to the velocity vector, well, what if B wasn't necessarily coming directly out of the page, but maybe it was slanted a little bit, let's say sort of pointing that way a little bit. It's kind of hard to think about this in 2D, but essentially the magnetic field does not necessarily have to be perpendicular to the velocity vector. It just has to have a perpendicular component. So the whole magnetic field doesn't have to be perpendicular, but the velocity does have to have a component that is perpendicular to the magnetic field for this situation here to arise. So this E does not have to be true, but B does. And you can sort of think about it a little bit in your head that there's no situation where you'd have a constant velocity like this where the electric field is not perpendicular to the magnetic field. Number 54, we are told that a conducting loop of wire that is initially around a magnet is pulled away from the magnet to the right, as indicated above. And we're asked about the direction of the force on the magnet and the direction of the magnetic field at the center of the loop due to the induced current. Well, let's first think about the direction of the magnetic field. I think that's maybe slightly easier. So if the loop is being pulled to the right, that means the magnetic flux through is going to be decreasing. If you think about sort of the magnetic field lines that are pouring through here, as we pull the loop to the right, less of these magnetic field lines will be crossing through it, so the magnetic flux is decreasing. And so if the magnetic flux to the right is decreasing, that means that the induced EMF will create a current that will produce a magnetic field that is pointing to the right, right? Because that would be resisting the change in the magnetic flux. Okay, and so using our right hand rule, we'll be able to figure out that a current in this direction will be causing a magnetic field that's in that direction. Actually, we don't really need to know that, but we do need to know that magnetic field that is created will be going to the right, so we can already eliminate B, D, and E. And now we're asked about the direction of the force on the magnet. And all we need to really think about here is that our universe tries to conserve energy, and we do not like to get in infinite energy loops. Well, it's physically impossible. And so that is to say that much in the same way that the magnetic field here that we created opposes the change in magnetic flux, the force that will be felt on the magnet will also be trying to oppose the change to the system. And so if the loop is being pulled to the right, then the magnetic force on the magnet will also be to the right because it will be trying to oppose that change, which is causing the change in the magnetic flux. So the answer choice here that is correct is A. Number 55, we are told that a square loop of wire carrying a current I is initially in the plane of the page and is located in a uniform magnetic field B, as shown above. It points to the bottom of the page. And we're asked about the initial rotation by the loop due to the force exerted on it by the magnetic field. So let's think about how the magnetic field will create a magnetic force on each of the four sides of this current carrying loop. So for these two sides here, since the current is in the same direction, or is parallel, I should say, to the magnetic field, then they will experience no force. And again, we know this because the force experienced by a current carrying, or a current, I should say, like a wire, is given by this formula here. And so that's a cross product right there. If you think about it, that cross product will yield 0 when we are parallel to the field. Okay, so then that leaves us to think about this top and bottom side. And there's the direction of the current. And if you use the right-hand rule here to think about these, what you'll get is that there will be a out of the page force up here and a towards the page force down here. So um, that must mean that this current, this side here is going to be sort of coming out towards us. The bottom is going to be sort of going away from us, which is to say, of these, only answer choice C correctly describes this. Actually, answer choice C is the only one that even puts the axis of symmetry correctly here, but everything here on this diagram is going to be correct. So the answer choice that is correct is C. Number 56, we're given a circuit shown above, and we're asked about the equivalent resistance of the three resistors. Well, we first want to start by thinking about the parallel resistors here, which are these two. And the equivalent resistance of two parallel resistors, in this case 2 and 3, is going to be given by 1 over 20 plus 1 over 60. And those are coming from here, of course. And this is in your formula sheet. And what you'd get is that the equivalent resistance of 2 and 3 is going to be 15 ohms. And we've actually seen this calculation in a previous problem. And then we are left with R1, and then it will be connected basically to a equivalent resistance of 15 ohms that's in series with it, which is to say that the equivalent resistance is just summing those two. And so what you should get is that the equivalent resistance is going to be equal to 50 ohms. And so the correct answer choice here is D. Number 57, we are shown a configuration of 6 particles, each with a charge of plus q, that are held fixed and are equally spaced around the circumference of a circle of radius r. And so we're asked about the electric field magnitude at the center of the circle. Well, let's think about the effect of each charge. What's going to be the electric field that it causes? Well, let's think about this charge here. It will cause a electric field maybe in that direction of that magnitude. But then let's think about this charge right here. It will create a electric field vector that's equal in magnitude but opposite in direction, which is to say those two will cancel out. So those two cancel out. Uh, these two will cancel out, and these two will cancel out, which is to say that all the electric fields cancel out, and so the magnitude of the resultant electric field at the center is going to just be 0. Number 58, we're asked about the same charge distribution from the previous question, but this time we're asked how much work it would require to bring a seventh particle of charge positive q from very far away, and then placing it at the center of the circle. Okay, well, so work in the context of E&M is given by Q times voltage, and more specifically, it's going to be big Q and times uh, here voltage. And we need to be thinking that we're going from very far away, which is to say we're basically going from out towards infinity and bringing in. And so the voltage at infinity, we just say is zero. But so really, we're just worried about the voltage of this point right here. Okay, so let's figure that out. Uh, since voltage is a scalar quantity, we can just figure out the voltage of each of these charges. So let's just start maybe with this point right here. It's given by this formula here that is on your formula sheet. And so that's to charge over the radius. But then if you think about it, every other charge here has the same sort of relationship or the same voltage equation that we just drew, which is to say, if we're adding all the voltages here, it really is just going to look like, we're going again from 1 to 6, it's just going to look like 6 times the voltage of just 1. So the overall voltage is going to be 6 times Q over 4, um, like so. So this is from just a formula from before, but we can simplify this to say 3 times 2. And then let's not forget that we're really asking about the work. So we can just multiply both sides by Q to get our work. And so the answer choice here, it's not going to be C. That looks close, but it's actually going to be D. Number 59, we're given a fun diagram showing equipotential lines produced by an unknown charge distribution. And then we're given 5 points here, and we're asked about what vector will represent the direction of the electric field at point A. So point A is right here. And so what do we need to know about electric field lines and equipotential lines? Well, first of all, they are going to be perpendicular. So that means that our electric field line will either be going in this direction or that direction. And then the other thing that we need to know is that electric field lines always point in the direction of decreasing voltage. And this is just a matter of thinking about this formula here, that E is equal to the negative derivative of V with respect to X or to position or something like that. So that's to say that our electric field will be going in that direction towards the zero. Since it's going from a potential of 5, it will be going down the potential. So the answer choice is A. Question 60, we're still working with the same equipotential line diagram from before, and we're asked about what point does the electric field have the greatest magnitude. So let's once again think about this formula right here that I wrote from the previous question, that is again in your formula sheet, which is to say that the magnitude of the electric field is going to be given by the derivative of voltage with respect to position. And so what that means is that wherever we see the biggest change in voltage in the shortest space is going to be the place where the electric field is the strongest. And so comparing this area here, this area, this area, and this area, and then finally this area, you can very clearly see that point B is where the sharpest change in voltage is happening. And so B is going to be our answer where the electric field has the greatest magnitude. Number 61, we are still working with the same diagram of equipotential lines from the previous two questions, and we're asked about how much net work must be done by an external force to move a charge of -1 microcoulombs from rest at point C to rest at point E. So work is given by this formula here that we've worked with a bunch of times before now. And so we need to be thinking about the voltage difference and the charges just given to us. But let's go back to the voltage difference. We're going from C to E, which means we're going from here to here, which is to say we're going from a potential of 10 to a potential of 20. So the change in voltage is just going to be final minus initial. 20 minus 10 is just 10, and that's positive. And so the work is just going to be given by -1 and then microcoulombs times 10 volts, and what you'll get is that that's going to be -10 microjoules of energy. But I would recommend just thinking real quick, does this make sense? Given that it's an external force, um, in the sense that, well, we know the magnitude is 10 microjoules, but is it going to be positive or negative? Well, let's go back up here. We have a charge of that is negative, so a negative charge, and we know that negative charges like to go to areas of higher potential. They're the opposite of positive charges, so they naturally will go towards areas of higher potential. So an external force that is pushing the electron or any charge of negative charge in that direction will be doing negative work. And so that means that our answer is consistent. That means the correct answer is indeed B. Number 62, we're told that one of Maxwell's equations can be written as the following, and then we're asked about what really this represents. And first, if you're wondering where this actually comes from, it comes from combining two different formulas. The first being that induced EMF is given by the change in the magnetic field. Um, and the other one coming from the fact that voltage, which is really the same thing as EMF, is going to be given by the negative line integral of E dot ds. So these are basically they're just going to combine these two and set them equal to each other, and so that's where we get this from. But let's read here the answer trace and see if they make sense. So a changing magnetic field produces an electric field. Is this what this equation is saying? Well, actually, yeah, it is going to be saying that. And the reason for that is that the magnetic flux is given by, well, something that looks like this. And so a changing magnetic field, so if this is varying with respect to time, then that means that it has a derivative that's not zero, which means it has an EMF, which means that the electric field here is going to be positive, or it's going to at least be not zero. So it's actually going to be A, but let's think about the other answer choices here. A changing electric field produces a magnetic field. No, this is basically trying to say the opposite of the previous one, but that's not what we see here. We're talking about the change in magnetic flux, not a change in electric flux. And we're producing an electric field, not a magnetic field, so it's not B. C, the net magnetic flux through a closed surface depends on the current inside. What they're really saying here seems to be Ampere's law, but that's not at all what is stated here. We don't see current anywhere in this formula. Then D is a net electric flux through a closed surface depends on the charge inside. Now they're trying to say Gauss's law, but again, we're not given anything about charge in this formula. And then electric charge is conserved. Um, that's not really stated here in this question at all, or in this formula. So A is correct, and all the other answer choices are not saying a true statement. Number 63, we are told that the plates of a parallel plate capacitor of cross-sectional area A are separated by distance d as shown above. Between the plates is a dielectric material of constant K, and the plates are connected in series with a variable resistance R and a power supply of potential difference V. And then we're told the capacitance of the capacitor will increase if which of the following is decreased. Okay, so a lot of words going on here, but we need to focus here on the end goal, which is that C increases, the capacitance increases if we decrease one of these values. And so the equation here of interest, and really the only equation that you need to be thinking about, is that the capacitance is equal to this formula right here from your formula sheet. Um, and then we also have this other formula that you might know of that goes like this, but we don't have to think about this at all. And why is that? Because the capacitance is not going to change unless the structure of it, which is to say its area and its distance and the dielectric in it, change. So this here, changing the voltage or the charge even, wouldn't really change the capacitance. It would just, this is just setting up sort of a ratio between the two that stays constant. So we can not think about this at all and only think about these. And from these variables here, the k, the a, and the d, only D, if we decrease it, will the C increase. So the answer choice here that is correct is D. Number 64, we're told that the currents in three parallel wires, X, Y, and Z, each have a magnitude of I in the direction shown above, and also Y is closer to X than it is to Z. And we're asked about the magnetic force on wire Y. I believe there's a very easy way to get to this question, and it's just by remembering that two wires going in the same direction, their currents, that is, two currents going in the same direction will cause a attractive force between them, while two wires going in opposite directions will go in opposite forces. So that is to say that on wire Y, since our wire X is going in the same direction, the current, that means it will be having an attractive force in that direction, and then wire Z, since the current is going in the opposite direction, will have a repellent force, which is also in that way. So it's very obvious that it's going to be towards the left. But even if we didn't have that, we could think about the right-hand rule and think about the magnetic field that is being caused. If we use the right-hand rule, what you'd find is that there's going to be a magnetic field caused by X here that is pointing out of the page. And then the same thing with Z, it's going to be causing a uh, magnetic field that's also pointing up. And so then finally we use the right hand rule again to think about a current going uh, down like this, and using the right hand rule, you'd see that the force would be to the left. So two different ways to get to the same answer. Number 65 is not a question I like very much because I think the wording is very unclear, but it goes like this. A physics problem starts a solid sphere has charge distributed uniformly throughout, dot, 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 it may be correctly concluded that, and then we're given here these statements that we have to think about. The reason I don't like it is because it's not very clear what they mean by distributed uniformly throughout. This could be throughout its volume or throughout its surface area. It's not made explicitly clear, but given the answer, which I know, in hindsight, uh, what they're talking about here is uniformly distributed throughout its volume. So we have to imagine here that we have a solid sphere that has, let's say, positive charge, and it's going to be distributed uniformly like so. Um, and then let's assess each of these. Electric field is zero everywhere inside the sphere. This is not true. I mean, for one, you can actually work out the Gauss's law that goes with this, and you figure out that that's not true. But another way to think about it is if we have a sphere that has a charge, the only way that the electric field is going to be zero inside of it is, well, in the case of a metal, because when we have a conductor, then the excess charge will sort of go here to the outer surface like this, and it will leave an electric field of zero on the inside. But since this is not a metal, because the charge is uniformly distributed throughout its volume, not on its surface, then it can't be that. Okay, B, electric field inside the sphere is the same as the electric field outside. Um, this is just not going to be true, especially because we have a charge. There's just no conceivable way in which that would be true if we have a net charge on this sphere. Even a metal will have a electric field outside, um, even if it doesn't have one inside. But those are not going to be the same. And also, the electric field changes on the inside and along the outside. So there's just no way this is going to be true. C, the electric potential on the surface of the sphere is not constant. This is not true. Again, if we have a uniformly distributed charge, then we can sort of treat it as a point charge as well. We can think of it like this. And so that means that every point along its outer surface will be an equal distance away, which means that the voltage formula that we could use from our formula sheet would be the same for all points along the surface. For D, the electric potential in the center of the sphere is zero. Again, this is not true because if we have a net charge, that means we have an electric field, and crossing an electric field takes voltage, or it causes a voltage difference, I guess is a better way to say it, which means that you're not going to find an electric potential of zero in the center of the sphere. And so that leaves us with E, which is that the sphere is not a metal, and this is actually something that we already came to the conclusion of earlier in the problem, and this is just affirming that. Number 66, we're given a circuit here with a battery, a resistor, a inductor, and a switch. And we're told what is the current in the circuit after the switch has been closed for a long time. So if the switch has been closed for a long time, that means we're sort of thinking about t going towards infinity. And what you should know about inductors is that although they resist a change in current, they're not going to be able to resist it forever, and eventually they act as if they're not even there. And so what that basically means is that the voltage across an inductor after an infinite amount of time is just going to be zero. So it's as if it was just a wire with nothing special about it. And so then we can just use Kirchhoff's rules here, which is to say that 12 minus I times 6, which is the resistor here, is going to equal to 0. Um, and so, again, we ignore the inductor because their voltage is going to be 0, which is to say that I is going to be equal to 2. And so the answer is C. Number 67, we're still working with the same circuit from before, but now we're asked about the potential difference across the resistor immediately after the switch is closed. So immediately after the switch is closed, that means that time is equal to 0, which means that the inductor is going to completely resist the change in current. And so if the switch was originally open, then originally the current through the circuit was 0, and after the switch is closed, because the inductor is going to completely resist the change in current, it will still be equal to 0. Another way to think about it is that at times equal to 0, the voltage across the inductor is going to be equal to 12 because it will be high enough to make it so that the current is still 0. So if the current through the whole circuit is 0, then the formula for a voltage across a resistor, which is given by this, will just tell us that it's equal to 0, and so the voltage is 0. That's answer choice A. Number 68, we're told that a uniform spherical charge distribution has radius big R. Which of the following is true of the electric field strength due to this charge distribution at a distance R from the center of the charge? Okay, so first let's think about, well, let's quickly look at these answer choices. Is it greatest when it's R is equal to 0? No. Actually, there the electric field strength is 0. Is it greatest when we're halfway through r. That's also not going to be true. It's going to be basically at the surface of the sphere. But let's just maybe leave this answer. Who knows? Maybe it's true. And then E, it's directly proportional to r squared. Um, just no, it's not going to be because we have a uniform spherical charge. That means we can approximate it by a point charge. And you should know that from a point charge, the electric field is going to be given by this formula right here. And so that right there is already telling us that it's definitely not going to be directly proportional to r squared. In fact, when we have a uniform spherical charge distribution, then we need to be thinking about two different electric fields, one inside of the sphere and one outside. And so this is given by the outside here. So I guess this is when, this is given when little r is bigger than big R. But what about inside when r is going to be, I guess, bigger than little r in this scenario? Well, we need to be thinking about Gauss's law here, and let's try to do this quickly. We don't have much time on this multiple choice. We'd be thinking E dot dA is equal to the enclosed charge over the vacuum permittivity constant, and so we can use a spherical shell like this, which will have that surface area, and it's equal to the enclosed charge. And the enclosed charge, we can just think about it as Q times since it's a uniform distribution, we can think about the volume of the little sphere that we're making inside of this divided by the volume of the big sphere that encloses the entire charge. And you'll see here that the pi's cancel, and so it leaves us with just r cubed, little r cubed over big R cubed times Q. So we could write it like this. And then when we simplify this, you'd see that the electric field is going to equal, or is going to be proportional here. Well, it is going to be equal to Q times R over 4 pi, the permittivity constant, and then big R cubed, like so. And so what you can see here is that in this scenario, when R is going to be less, a little r, I should say, is less than big R, that E is indeed proportional to R. And so the correct answer choice here is going to be D. Number 69, we are given one of these fun scenarios where there are charge distributions moving around because of induction and conduction and stuff like that, and I think these are always kind of fun to figure out. So we start here with a negatively charged rod that's brought near but does not touch, that's important, the initially uncharged electric scope shown above. We just need to know that this is a conductor here that allows for charge to move around. Um, and so when it's brought close, the leaves here spring apart. So that's what's happening in one. Then we bring and we touch our finger on the electroscope and the leaves collapse. And then when we move both away our finger and the rod, they go back to being sort of half spread apart like this in three. So we need to be thinking, what's going on here? And let's follow the charges as this is happening. So initially this is uncharged, which means this has an equal amount of, for our intents and purposes, we can think of an equal amount of positive and negative charge, which is true, but let's imagine that they can move around. In reality, only negative charges can move around, but for our purposes here, we can think about the positive charges moving around. And so the positive charges will want to get close to the negative rod, and the negative charges will want to get away. Okay, so that's what's happening here, is that the positive charge gets close, and the negative charges go away. And so let's just show overall it's still electrically neutral. Okay, but then what happens when we touch our finger here? What happens is that basically many of these negative charges here will see that, wait, I can get further away from this negative charge, which I'm repelled to, by going through the finger here. Okay, so you're going to have a bunch of negative charges exiting through the finger, into you. And what's going to happen is that basically, I'd imagine you still have a positive charge up here trying to be attracted to that rod, or it is attracted to that rod. But here you'd maybe have an equal distribution of positive and negative, and that's why it's back to being attractive like that. So we've had basically one unit here of negative charge leaving the rod through contact with the finger. But then we move away both the finger and the electric and the negative rod, and so what we're left with is a slight abundance here of positive charge compared to negative charge, which is why the leaves still basically, or the leaves here of the electroscope, will spring apart still a little bit. So now going to our answer choice, and I mean, I would recommend as a good AP Physics student that you try to figure out these problems before looking at the answer choice when you can. So going here, it seems that in number one, we have a negative charge on the leaves, And then on the number 3, we have a positive charge. And so it's going to be answer choice D, which is correct. Number 70, we are told that a sheet of copper in the plane of the page is connected to a battery as shown above, causing the electrons to drift through the copper towards the bottom of the page. Let's actually just think about that real quick. If the current is going up the copper sheet here, uh, keep in mind that when we say current is going in one direction, really means that the electrons are going in the opposite direction. Okay, so this makes sense here, the statement. Okay, so the copper sheet is in the magnetic field B directed into the page, and P1 and P2 are points at the edges of the strip. Which of the following statements are going to be true? So let's think about what's happening here. We have electrons that are moving down like that. As we've been told, they're drifting towards the bottom of the copper sheet. And what this is actually called is called the Hall effect, which maybe you didn't learn in your class, but you should have enough physics knowledge to be able to figure this out without necessarily knowing what the name of this concept is. If we have charges that are moving in the presence of a magnetic field, then surely they must be feeling a magnetic force, right? And we can tell because of this formula right here and understanding the right hand rule. So using the right hand rule, we'd be pointing our fingers down in direction of the movement of the charge, and then we curl our fingers in direction of the magnetic field, and we'd actually get that the force is towards the right, but keep in mind we're talking here about an electron which will experience an opposite direction force, which means it will be experiencing a force to the left. So we'd have a buildup of electrons here on the bottom left of the sheet, which is to say that we have a negative voltage on the left and a positive voltage on the right. And so going back now to our answer choices, B is correct that P2 is at a higher potential than P1. And with that, congratulations, you finished the multiple choice section of the 2004 AP Physics, Electricity and Magnetism exam. Thank you so much for watching the video. I hope you enjoyed it, and be on the lookout for hopefully more videos like this in the future. If you want to see more, subscribe, and if you enjoyed this video, please leave a like and let me know any other video I should make related to physics.